our math project is the maximum and minimum of functions of two variables, and I'm Maya Pulliam, and this is also Sam Yoseph and Fiona Zabel. And this is our abstract. We're not going to go over it in this video, but if you would like to read it, you can pause.
All right, so to begin talking about the background, we have to understand how to calculate extrema. And our first step in doing that is identifying the critical points within the function that we're given. But because we're working within a three-dimensional space, it becomes more complicated as our points are given to us in the form of z of x, y. So to overcome this difficulty, we can find the gradient of the function that's given by taking the partial derivatives of each point and then equaling the resulting equations to 0 in order to create a new vector field.
In some problems, we are also asked to optimize the situation given a constraint condition, for example, maximum of f of xy based on g of xy. And in such a situation, we use the Lagrange multiplier such that the gradient of f equals lambda times the gradient of g when lambda is some constant. And based on this setup, we can establish a system of equations to solve for lambda and then find the critical points for extrema. And we can then find the discriminant d of xy to establish if the point is a maximum, minimum, or a saddle point.
So we would like to go through how do you find partial derivatives. So to find a partial derivative with respect to x, you can take the derivative as you normally would and treat y as a constant. So you can see in the first example, the partial derivative with respect to x of f of xy equals x squared y. The partial derivative of f of x, which would be denoted as del f over del x, would be 2xy, because you would take the derivative of x squared, which would be 2x, and multiply it by the constant y. To find the partial derivative with respect to y, you would take the derivative and treat x as a constant. So similarly, we would take the derivative of y with respect to y, which would be 1, and you multiply it by the constant x squared.
To determine if a point is a maximum, minimum, or saddle, we use the equation of del squared f over del x squared times del squared f over del y squared minus the quantity of del squared f over del x del y squared as the discriminant, using points we found in solving systems of equations to plug into each respective partial derivative. If both the discriminant and the second partial derivative of x is greater than 0, then we can conclude that the point is a local max. This will provide the greatest value of f within the given constraint. If the discriminant was greater than 0, but the second partial derivative of x was less than 0, then we can conclude that the point is a local min. This will provide the least value of f within the given constraint. If the discriminant happened to be less than 0, then the point would be a saddle point. So we can conclude that such a point is not a local extremum. If the discriminant happened to be equal to 0, we simply cannot come to a conclusion.
So in our first problem that we looked at, we were to find the stationary points of the function z equals x cubed y squared times the quantity of 12 minus x minus y, which satisfy the condition that both x and y are greater than 0, and then to investigate its character. So if we're breaking that down, firstly, we're finding critical points, and then we're determining whether they're maximums, minimums, or saddle points. So in this particular situation, we can find the gradient of the function, which means that we're finding the derivative with respect to x and then the derivative with respect to y as two separate functions to create a vector field. And so you can see we take the derivative with respect to x, and that's 36 x squared y squared minus 4 x cubed y squared minus 3 x squared y cubed. And we take the derivative with respect to y, which gets us 24 x cubed y minus 3x cubed y squared minus 2x to the fourth. So what we need to do is set that gradient equal to 0. So we have a system of equations at this point where we set each of the partial derivatives equal to 0, and we can solve that, and the point that we get is 6, 4. Now, if we plug that into our discriminant formula, we find that the discriminant is greater than 0, but the second derivative with respect to y is going to be less than 0, and as a result, we can determine that this point indeed is a maximum within the function. So for our second question, which was an optimization word problem where we find a rectangular parallelepiped of a given volume V having the least surface area. So based on that, we can determine that f of x, y is going to be our our function we want to optimize because we want the least surface area, so we're looking for a minimum. And g of xy is going to be the volume because it's our constraint function and what we can't change. So we take the gradient of each of those, and then we can set them equally to each other, where the gradient of f is equal to lambda times the gradient of g, where lambda is equal to some constant. So when we solve this system of equations here, we find that w equals h equals L. And as a result, we know that the length is equal to the height is equal to the width, which would describe a cube. So then we can say that a rectangular parallelepiped with a given volume V has the least surface area when that rectangular parallelepiped is a cube.
So for our third problem, we were to find the stationary points of the function z equals 2x cubed plus xy squared plus 5x squared plus y squared. So for our solution, we took the gradient of the function, which gave us the derivative with respect to x, which is 6x squared plus y squared plus 10x, and then the derivative with respect to y, which is 2xy plus 2y. And we set each of those partial derivatives equal to 0, and that gave us y squared equals negative 2x times the quantity of 3x plus 5, and 2y times the quantity of x plus 1 equals 0. And from there, we were able to get 4 critical points. And from the first partial derivative, we were able to get the point -1, +2, and -1, -2. And from the second, we were able to get the point 0, 0, and -5/3, 0.
Similar to the first problem, our fourth and final problem is to find the point of extremum of the function z equals x squared plus xy plus y squared plus x minus y plus 1. To do this, we first have to find the gradient of the equation and make them equal to 0. And this will give us our critical points. To find the gradient, as previously explained, we're going to take the partial derivatives with respect to x and then do the same but with respect to y. After doing so, we're left with a system of equations. 2x plus y plus 1 equals 0, and x plus 2y minus 1 equals 0. In solving the system of equations, we find the point -1, 1. And to proceed further, we then need to determine the character of this point. To do this, we have to find the second partial derivative with respect to x and the discriminant. Since both are greater than 0, we can determine that the point -1, 1 is a minimum. Thus, the point of extremum in the function z equals x squared plus xy plus y squared plus x minus y plus 1 is a minimum of -1, 1.
We'd like to thank Dr. Goldenberg for all of his help on this math project and the guidance he provided us during this process. We'd also like to thank all of you for tuning in, and especially for supporting Ingenuity even in these really interesting times, and for helping us pull off this senior symposium even from home. Thank you.